Kind of. It like made sense. I just have to learn this the plot. Yeah, I was doing it. I actually made sense. I don't know.
Yeah, that's this one's yeah. You can, I bet, you can turn it in though. Like,
Yeah, I'm gonna make sure that I don't not getting stuff good.
All right. Still trying to get us going here. All right, so I am trying to print out a polyatomic PDF, which is apparently a difficult task to accomplish, so I'll work on that because we're going to need that, so that's why I'm late. I'm going to have to leave you again. And so now we need to get into naming polyatomic compounds, but again, I'm trying to hand you a sheet, and all the good ones are behind paywalls, so it's taking a lot longer, and I was stupid and didn't remember till right before your lecture. All right, so this is what we're going to be doing, and so I won't make you guys memorize it. Again, I'm going to hand you a sheet eventually as soon as I can get it printed and not something stupid like that. And the printer's occupied, so now we're never going to get it printed probably. But so the point is, and again, right, this is why we want this chart, because we're moving at a fast pace, so normally, you might be expected to memorize these, but not for our course, right? All you want to recognize is, oh, what is a polyatomic? And then find it on the chart that, like I said, will be given to you shortly. And so I'll just point out some other polyatomics that are common. So obviously hydroxide comes up a lot. So this would be in like potassium hydroxide. So this is used, you can make soap with it. So, and of course you just name it, right, potassium, and then you name the polyatomic hydroxide in this case. Obviously we've seen some carbonates, I believe, or you will see carbonates, pretty common. Acetate, so this is one that always throws off students because it's written in two different forms. And so sometimes it's just C2H3O2 with the negative charge, or it's written as a CH3COO. And we could draw out what acetate looks like. So this is acetate, the little structure. So this is an organic molecule. It's actually acetic acid would be the acid, but it's kind of jumping into our last week when we'll talk about this in more depth. So that just translates that. Nitrate is pretty common. You see a lot of metal salts with nitrate. Of course, that's NO3 with a -1 charge. And then notice ammonium is one of your few ones that are positive charged. So this is a cation. So ammonium, I can draw out the structure. And so again, you'll get here eventually. But this is ammonia, so it's this tetrahedral structure. And then it has a plus charge, so you just indicate that like that. But again, right now we're just kind of appreciating the formulas. Phosphates are pretty common as well. Just kind of give you an idea. And then watch out for these chromates. These can confuse people too. A common compound you'll see potentially is like potassium dichromate. So K2Cr2O7, 2-. And again, you just have to look at your chart here to figure out, oh, okay, this is a polyatomic, and then you can name it as dichromate. Oops. And then you would not put the -2 charge in there in the compound. So obviously just saying -2 here means I put 2 potassiums there to balance it. So still just trying to make neutral compounds. So then like phosphate, right, -3. So an example would be sodium phosphate. And, you could kind of put in parentheses to help, but not necessary unless, of course, you need to make multiple equivalents. sodium phosphate. All right, try the practice real quick, but I am going to go back and try to print at least something so you guys have a reference for class. So I'll be right back and try to print again. It's fine as long as you're not trying to make like multiples of them. Oh, yeah. All right, that will be helpful. So take another minute or so if you need.
This was, I didn't understand this.
Oh,
This was
yes.
just like in Tootsie.
All right, who wants to give us this one? Yeah, Sarah.
I don't know if this is right, but is it potassium dichromate?
Yep, so potassium dichromate. So again, just recognizing the chromate, so that's good. What about this one? Yeah, Jennifer. Yeah, magnesium hydroxide. Excellent. And then what about this last one? Yeah, Braden? Iron, but then what does iron need though? What's a little different about iron than like magnesium? Anybody remember what we need to add? Yeah, iron 3. So don't forget those Roman numerals. Let's see. Chat remember today. So excellent. So yeah, make sure you put iron 3 nitrate. Yeah. So it goes back to any of the transition metals. So I think we covered it, but yeah, let's just recap, right? So remember we said that for these type 2 metals, these multivalent ones, these are going to be any of the transition metals really, unless we mark them as the exception. And so the exceptions were like zinc and silver. So remember we had kind of marked them. So zinc is always 2+, so we don't need to say that. And silver for our Gen Chem purposes is always 1+, but if you go on the research world, silver can take other oxidation states. It's just, for naming, it's always 1+, so we don't need to indicate, again, in our class. But then everything else in our transition metals, so right, iron is at least listed here that it has 2 and 3, but it could be 1, it could be 4, so iron can take other oxidation states. And then obviously, right, all these other metals, they just didn't list them. And then we mentioned, right, those other ones. So the other exceptions for the ones that we have to use the Roman numerals are lead, thallium, and tin. And those are in the main group. Oh, they're not here, but they would be listed in this area. Yeah, anytime we have those, we need to use a Roman numeral. Yeah.
How do we know to use iron 3 in this one instead of iron 2?
So this one, we have to base it off of the nitrate. And so we can go back, so we look at nitrate on our chart. So that's NO3 with a -1 charge. And then there's 3 of them. So then we know iron has to be 3+ to balance that out. So same sort of thing as before, right? Again, you're just balancing out the charges. And that's why I'll let you use the cheat sheet, right? So you can look at it, refer to the charge, and then you base the metal charge off of that polyatomic charge. And we'll probably have time for more practice today. All right, so we got our polyatomic sheet, yay. So I think we're ready for, well, before we do practice, one little bit. So the last little bit to cover is this naming of when they're complex to water. And so let's pull up some examples. And so looking at this, so the other thing that we want to emphasize is this is like a phenomenon that happens sometimes. And again, it's just like one of those things, and you have to really examine the crystal structure. And so let's look at nickel chloride. And so nickel chloride, if you look at it, and oftentimes, again, if you play with it in like a Gen Chem, maybe like high school setting, you have this nickel chloride hexahydrate, and it's generally green. But really, anhydrous nickel chloride is, of course, yellow. Well, not of course, you wouldn't know that unless you actually play with them. So, right, if you compare your anhydrous nickel chloride, and anhydrous, of course, means no water. So it's this nice yellow powder. And then there are purification methods to actually be able to convert the nickel chloride, which is again complex, to water. And so what we want to emphasize is obviously how to write the formula, but I'm also trying to show you, yes, it is complex. And so this is our, it should be 6 of them. I'm trying to find where the 6 waters are. Yeah, so this is interesting because this is really the true structure of the nickel hexahydrate. And so if we look at it, and so this is also what you look for. And so in this case, so it kind of depends again on each like molecule. So in this case, we have 4 directly complex to the nickel here. And again, right, we're taking a crystal structure, which basically means like they took a solution of this nickel chloride, right, the hexahydrate. You let it grow and let it sit, and then it forms these crystals. And then you take those crystals, you shoot X-rays at them, and then you get, right, your at least picture of the solid state. So that's also key, right? This is a solid state picture, so we don't have any dynamic behavior. But then how we get to 6 is that there's 2 more water molecules floating around and kind of encapsulated by the crystal structure. And so to write this, we can use our prefixes, and then we'll talk briefly about this hemi and where, again, it would come into play. And so we just use this little dot so we can write our, let's say we want to write our compound for nickel chloride. So we can say nickel, and of course it's 2, chloride. And then you just have this little, then you say hexahydrate. So you use your prefix, and then you put how many water molecules. And then we can translate that back to our chemical formula, and then we just use a little dot here to mean that it's complex to 6 water molecules. So this is the same thing. And then we have this hemi. So hemi is when we have half an equivalence. And so that would be, and I'm just going to make up a scenario, but let's just say you had like 1 water molecule, again, crystallized in our crystal structure. And I'll just, again, I'm making up this tungsten 3 compound. It probably doesn't exist, but I'm just saying, right, again, it would be in the crystal structure. We would notice, okay, we have 1 molecule of water for every 2 of this compound. And so for this fake example, and so I'm calculating the oxidation state based off of the 3 chlorides it's attached to. So this is tungsten 3 chloride. And then now we can use that hemihydrate. And that's where you get the half equivalent of water, right? It's just the ratio of the crystal structure. Does that make sense for these kind of water complexes? And so we'll do an experiment in lab, I think, where we determine how much water is complexed, to magnesium sulfate salts. And so I just want to at least show you these magnesium sulfates, again, how they look. And so this is interesting, and why we do the lab is because there's a few known variations of these hydrate salts. And so again, you can just appreciate that you can also get different ratios of water complexing, right? So these are all considered different little complexes in some ways, right? We have the anhydrous form of magnesium sulfate, monohydrate, dihydrate, et cetera, et cetera. So again, just kind of cool to appreciate what's going on. All right. Questions about anything? I think your class is actually on pace pretty much now. So now's a good time. I think we could do some, oh, one last thing. I forgot the naming of acids. And so the acids is one of those you just kind of have to learn. And so notice, right, we have a lot of our simple acids like HCl, HI. They all follow that pattern of hydrochloric acid or hydroiodic acid. And then, of course, you can see hydrobromic is on here. And then any other funny acids, again, follow the same kind of pattern where you have, so you can have cyanic acid or hydrocyanic acid, again, just adding that hydro and changing the ic. And then we have our other types of acids, so nitrous and nitric acid, depending, again, whether it's related to the nitrate or the nitrite. But usually in lab, you'll just encounter nitric acid and phosphoric acid, so that's pretty common. Same with sulfuric acid, H2SO4. Then you probably won't work with any perchlorates acids. But so just kind of go through this naming. So you just kind of have to learn, right, these other ones. You just have to know that nitrate is nitric acid and phosphate goes to phosphoric acid. And then sulfurous, sulfuric, etc. Just kind of, again, learn those. And obviously HF, right, hydrofluoric. So those all follow that same pattern. All right, let's do some naming practice then. If I can find my tab. So let's just start off with, let's at least do the first 5 and kind of see how that goes. All right, let's start going over them. What do we get for the first one? What'd you say? Yeah, molybdenum, and I might have missed. And then what else do we need in there? So molybdenum sulfate, but then what's the significance of molybdenum and where it is? If I could find our periodic table. So, yeah, transition metals. I don't know who said that. All right, it's in our transition metals, so we need to specify its oxidation state, though, because it's one of those multivalent metals.
You can choose that, right? You can choose which one you want to use, whether it's the +6 or the +4.
Well, we can't choose it. We have to base it upon our sulfate formula, right? So, okay, we have molybdenum sulfate so far. We know we have 3 of them. So what was the charge on sulfate? Yep, so -2, so -2 times 3 is, so then what does molybdenum have to be? So +6, so molybdenum 6 sulfate. So just don't forget that Roman numeral there. Yeah, so basically for all transition metals, so again, like, unless it's zinc or silver, we're saying. So what about this next one then? What do you think? Yeah. Check the Roman numeral. So titanium, nitrate, just double check your math there.
Oh, yeah.
Yep.
Okay, cool. I wasn't sure because it wasn't
Yeah, as long as it's just within reason. So basically, like, I know it only lists a few ones, but it is not an exhaustive list, so. Yeah, so again, base it off of this, the formula. So excellent, titanium 3 nitrate. And so again, right, you look at your chart, nitrate, we can see, okay, NO3 with a -1 charge. So then -1 times 3 gives us -3, so of course titanium has to be +3. Did we get tripped up by this one? I didn't talk about this scenario. It's a little funny. Any guesses on how to name this one? Sarah, go for it.
Sodium hydrate?
It's actually hydride, but that was a good guess. So hydride. That's right. It still takes the "ide" ending. And so this is funny. And so it's just a special case. And so usually, right, hydrogen is always +1 unless it's bound to a metal. So hydrogen with a metal, though, is called a metal hydride. So that's just the generic term. And then hydrogen is considered to be this -1 oxidation state. And so that could be with like aluminum hydride or iron hydride or any of these metal hydrides. And this starts to get into like, eventually storage chemistry and like solid state hydrogen storage if you are interested in that research-wise. But yeah, otherwise, when you see hydrogen with a metal, know that it just acts kind of like a halogen. But no, it's not an acid, sodium hydride. And actually, so these hydrides too are pretty flammable. I'll put a picture. And so they're going to react with acid, or with water. So it's just a hydride complex like that. But yeah, pretty water sensitive. And so it can light up in air. So it ignites in air, which if you read this Wikipedia, so if you have like 95% sodium hydride, that's super flammable, like residues of that can start, trash fires in a research setting. And then oftentimes, so it makes this little, under the practical considerations, it mentions how usually it's sold in like this weird mineral oil thing. So it's like this it's like a gray powder, but like covered in mineral oil. So it's and that's easier to handle, but then it's covered in mineral oil and trace mineral oil anyways. And so then it makes sodium hydroxide, of course, after it reacts with water. And then it releases hydrogen. And so that hydrogen released is actually what makes sodium hydride fires or any sort of metal hydride fires dangerous. So again, going back to the hydrogen storage. But if it's reacting and on fire, then you have, the extra hazard of like hydrogen being released, so that can cause more little mini explosives. So that was just fun fact of sodium hydrides. All right, back to naming. What do we get for this next one?
Is there a figure in front of that 7 that's significant in between the
It's-
subscripts?
It's just that little dot to show that it's complex. Do you want to give us the rest of it?
No.
Break it down. What's the first part?
So PE is going to be, that's going to be, it's going to be beryllium.
Beryllium.
Beryllium, sulfur, oxide.
Oh, but remember, you got to find your polyatomic. And I probably misspelled beryllium.
So that's going to be a sulfite.
So
if I'm not mistaken. Beryllium sulfite.
beryllium sulfite.
Yeah, seven waters.
So how do you say that? What, do you remember the prefix for 7? Yeah, Crystal?
I was gonna ask, are you gonna get a printout of the
I wasn't planning on it. But you could print it out. I mean, do people really want this printed? Is that something that a lot of people need? Okay, so maybe I will print it out then if a lot of people need this. So I will work on that. Probably while y'all are quizzing, I'll print this out then so you can have that. But yeah, hepta is R6. Sorry, and I was going to fix my beryllium. 7, sorry. Hepta hydrate. So it's 7, yeah, it's hepta. What about the 5 here? Sarah, you want to go for it?
Is it iron 2 phosphate?
Excellent. So iron 2 phosphate. And so there are a few ways to get to iron 2. Maybe, at least for me, the most obvious one was if you do the reverse swap trick. you see that 3 does match for phosphate, so then yes, it has to be 2. Or, again, just kind of go through the math. So you can look up phosphate, so -3 times 2, -6. So then iron has to be 2 plus. So excellent, iron 2 phosphate. And then let's do 6. So take a second, see if you can figure out what 6 is. That one maybe looks scary, but break it down. So do we find the name for this one? Yeah, I don't know who said it, but ammonium acetate. So, right, that was good. So you had to kind of recognize, okay, there's my ammonium. Remember ammonium. And then we have, right, the C2H3O2. Again, don't let that scare you, intimidate you, but excellent in recognizing, right, acetate. And so that's kind of a good rule for our class, right? We probably won't see too many organics like that, but, same sort of thing that you just recognize, the polyatomic. All right, I think we've covered about everything, yeah.
Can I ask for just one more example with something in relation to like to number 5, just where we are dealing with the subscript and we're having to identify.
You want to try 8 then? Because that one looks funky.
Yeah.
Do we get an answer for this one? Yeah, go for it. Yeah, manganese 7 phosphate. So that was another one where the swap trick was pretty useful. So right, again, just when you reverse the numbers, you want to compare, does -3 match with the correct charge of phosphate? Yes. So that means that 7 is our charge for manganese. And again, just double check the math, right? -3 times 7, -21. 7 times 3, +21. So that all looks good. All right, any other last minute thoughts or ideas?
Can you walk through the reasons for that one more time?
So depends, do you like doing the reverse swap trick? Because the swap trick is just kind of the fast way to do the algebra, right? Because otherwise you're going, okay, I'm going to look up phosphate, right? You look it up in the chart, PO4, 3 minus, and then you go, well, if each one of these phosphates is a -3, so -3 times 7 gives us 21, right? And then you can solve algebraically, well, there's 3, and you have to get to 0, so this has to be 7. But that's what I was saying, the reverse swap trick, right, where you just take the little subscripts and put them back over here, that should match as well, right? So we're saying, put the -3 up here. Does that match with the charge of phosphate? Yes, so then we don't have to multiply it or anything. And then we can just bring the 7 up, and again, that solves for the algebra. Any other last thoughts, questions? All right, I'm feeling good at least about our pace and that we've covered everything. So again, just ask questions after the quiz if anything comes up. We're happy to help. All right, otherwise I think I have the quiz ready to go. So I'll go ahead and hand it out. You can use your notes and stuff. If you need to take a break, before doing the quiz, that's fine. And then I will print out the prefixes so you can have that to reference for later. Oh, you can always leave after the quiz. So if you want to run away really quickly before I make it back, you can just turn in the quizzes. Hopefully it doesn't take me that long to print. Otherwise, like I said, I'll be back to answer questions. Yes, you can use all your notes, right? Old homework if you need.
Is that going to be the same for the exam?
Yes, the exam will be open notes for us, yeah.
Oh, it's 1 page.
Front and back there. Yeah, so take your break if you need to take a break, but yeah, open book, open. Right, just don't ask Google for the answer.
Open book.
Yeah. But just no Googling, no asking your neighbor either what their answer is.
Can you use the book?
Yeah.